guys, welcome to a new video. I want to begin things by first going over some of the generalized anatomy of the ear, and then we'll look at some more depth and detail specifically on the inner ear. But before we get started, let's kind of go back and divide up our ear into three main anatomical regions and go over some of the primary things involved in this. So the first, let's draw a line right here signifying our external ear, which is all mostly there to collect sound waves and transmit them to the next part, the middle ear. And the middle ear here is all about taking and amplifying sound and acting as a resonance chamber. And then we have our inner ear, where all of our sense organs are, the sensory receptors, the specialized neurons, whose job it is to turn the sound waves and the things we're hearing into very specialized neurological impulses that the brain can understand. So what I'm going to do is clean this off, and then we're just going to look at some basic structures, starting off here with our ear lobes, which we can refer to as the pinna or the auricle. And that will lead us to a tube here, which is the external acoustic meatus. The external acoustic meatus, which is the tube here that will lead to this structure here called the tympanic membrane. And the tympanic membrane will become very important as we call this the eardrum. Now, these structures here in blue are all in reference to a set of bones called the auditory ossicles. These are three of them. There are the, and I'm going to use now green to highlight that after I do a little bit of erasing here and kind of come back to that. We're going to clear that out a little bit. And let's use green and start showing you guys the malleus, the incus, and the stapes, these three bones. Now that will become very important in the hearing process. And lastly, the structure that we're going to be looking at here, shaped like a snail shell, is the cochlea. And these will all come into great importance for us as we move forward. Now, just a couple of neurological structures we want to mention. There are the two branches here of the vestibulocochlear nerve, the vestibular branch, and then this one, which is very important for us today, is called the Cochlear Branch of vestibulocochlear nerve, cranial nerve number 8. So what I want to do here is if I were to clear this off, and if we were to come in and say, well, let's focus in on our little cochlea here, and we were to look at this in an in-depth way, what we want to do is imagine that we took this snail shell shaped structure and we unrolled it. And that's what we're going to do here. So let's take this and draw it out and imagine we have an unrolled cochlea. And we might see something like this. I often refer to this as a sausage. Now, we're also going to take the middle part here and draw that, a tube and a tube, to help us visualize what's going on. We're going to draw a structure here that looks like an oval and a structure here that looks like a circle. And this would be our inner ear, the cochlea, if we unrolled it. Now, the inner ear, the cochlea, is, and all the other inner ear structures, have two major labyrinths that make them up. A bony labyrinth and a membranous labyrinth. And these are two different areas, parts, subdivisions of the inner ear. The bony labyrinth and the membranous labyrinth have a fluid between them referred to as perilymph. So the perilymph fluid would be located here. And inside the membranous labyrinth, there is a fluid called endolymph. and they are separated by different membranes, so we would be able to have an idea of the different fluids. And this will be rather important in the hearing process. So what I wanted to do here, let's imagine we have our stapes, and we're going to draw the stapes here like a little toilet plunger. This is actually, the way this is drawn is actually thanks to one of my Facebook page followers who sent me a drawing of her cochlea, so I'd like to give special thanks to her, but it acts very much like a plunger, and I use that analogy all the time. So what we want to imagine here is, for this, we have this window, an opening in the bony labyrinth, and this is the oval window. And the oval window has the stapes sitting on it. And the stapes is going to vibrate. It's going to begin to vibrate as it pushes in and out and vibrate at the oval window. And when this happens, it will create a pressure wave inside this fluid. And this duct that this is occurring into is called the Vestibular Duct, or sometimes referred to as the scala vestibule. And what happens is this pressure in this perilymph of the vestibular duct is continually being brought through these ducts here. And it's transmitted to another duct down here at the bottom, and this one is the tympanic duct. And the pressure waves will continue, and what they're going to do is they're going to hit this little window here called the round window. And there is a small little membrane here that will cover this up. And I will show you another drawing here in just a minute, and kind of what happens as we take this process and we kind of simplify it a little bit. I'll show you kind of what happens here. So what we're going to do at this is, if we understand that these pressure waves are going through here, well, there is one more duct we have not talked about. I'm going to use a different color here, and we're going to make sure we can see the Cochlear Duct. And this is important because in the cochlea, this is where hearing will take place. You see that the Cochlear Duct has a floor and a roof. And this floor down here is actually referred to as a basilar membrane. And the roof up here is referred to as a vestibular membrane. And the endolymph inside of here, what's going to occur is, as the pressure waves that are coming through these ducts past this, it will cause undulations to this basilar membrane. And what's going to occur here is, on the basilar membrane, if we took a look at this, the basilar membrane here we used, and we were drawing this basilar membrane at the bottom, holds a series of cells here, and inside these cells there is a very important set of specialized neurons here called hair cells. And hair cells are mechanoceptors. What does that mean is, when they are distorted, when they're vibrated on, it will stimulate them and alter the rate of neurotransmitter release from these cells. So that will let the brain know, via the cochlear branch of the vestibulocochlear nerve, that we have been exposed to sound waves. So to do this, there's an overlying structure called a tectorial membrane. And this works much like an old-timey telegraph that you might see on the old kinds of Western movies, or Western movie, the Old West and stuff like that. So you would see these things coming together and colliding. So what happens is, when this membrane here undulates, the tectorial membrane and these hair cells will collide with each other, creating a rhythmic set of patterns that will send signals to the brain and let me know that I'm hearing. And it's a pretty fascinating mechanism. So there are supporting cells, and there are a variety of other cells, but it's the hair cells that we're most interested in here. So also that basilar membrane. So when they come together. So if I were to take this cochlea and draw it one more time, but a little bit more simplified here, and imagining that we have another duct, and I'm just going to put this as we'll go and draw this guy as this little yellow line in the cochlear duct here. What we want to imagine is that we have our three bones. So to do that, we have our tympanic membrane, our malleus, our incus, and then we have our stapes. And our stapes is sitting on a structure here called the oval window. And when it's distorting that, that will create pressure waves in vestibular duct. And what will begin to happen is you will start taking your cochlear duct here and you will begin to distort it. And these pressure waves will continue on, and also distortions will continue to happen to the cochlear duct, right? It will continue to be distorted. So as this, what you would notice is as I push this guy in, I'm going to see my round window pushing out. And it's going to distort, it's going to take those distortions and pressure waves and dissipate them to prevent an auditory echo. So what you've got here is your round window dissipates pressure waves to prevent the auditory echo. So if we wanted to recap this and take this to us and really begin to understand it, let's break this down once more. So I made this guy a little bit smaller again, and if we take our sound wave, let's use a brighter color here. Let's pick purple, and let me grab this little snag on my purple colors here. And so a sound wave, which does have a waveform, I know that purple is a little bit darker. Let me pick that color there. That'd be a little bit better for purple. That might work for us. Is this sound wave enters into the auditory canal. And it's going to hit our eardrum, and that's going to vibrate. That's going to vibrate the auditory ossicles, malleus, incus, and stapes. The stapes is going to do its tulip plunger thing, creating pressure waves that go through the cochlea, undulating the cochlear duct. Once that happens, it will stimulate, guys, this structure, what's called the organ of Corti, and it's going to create and act much like one of those telegraphs beginning to vibrate and collide together. And the hairs, the cilia of the hair cells, will begin to be stimulated. And this will alter the neurotransmitter release, beginning to let my brain know that I'm hearing and how intense the sound is. Certainly tell me about the frequency of the sound, the wavelengths, etc., and the quality of the sound. So I hope this basic little diagram here helped us begin to see what is happening. I know it was a rather short video on the hearing process, but I hope that you guys understand it now a little bit better. And if you would like to see other topics of me, please let me know. Comment below in the comments section. Let me know what you would like to see. And please don't forget to subscribe to me, contact me. Let us know what you think. I'm always here to help students understand complex concepts. So thank you and have a wonderful day.